if you launch CATIA, and if you go under Start, Mechanical Design, and then go to Part Design, then enter the name for your part, whatever you want, and OK that. Now, choose any plane that you want out of the original planes. I go with the XY plane, and then click here on the Sketch command. There we go. Now, let's draw something very simple first. Let's say a rectangle. Exit the Sketch Workbench. And now, the extrusion command here is in this sketch-based toolbar, and that is the top one. Now here in CATIA, it is called Pad instead of Extrude, but that's the same thing. So you first need to have the profile selected. If when you get out of the sketch environment, it is orange, and orange means it is selected. But if you click somewhere outside the sketch, then it is go unhighlighted. So if you want, you can click on it or select it from under the spec tree. So this is sketch, click on it. So now it is selected. Now click on the pad. And when you do, a preview of the extruded version, which is a cube, a box, will appear. Now this pad definition or extrude definition window has a lot of options, and we're going to go over them right now. So first thing is type. How would you like to do the extrusion? Is it by a dimension? Or there is up to next, up to last, up to surface, and so on. So for the moment, let's just focus on the simplest of all, dimension. So we provide a dimension, and we also provide a direction. You see this arrow here shows the direction of extrude. So it is upward. Can I extrude the sketch downward, which means below the XY plane? Sure, all you need is click on the reverse direction, right? Or you can click on the arrow itself. So you can reverse the direction of extrusion. It's perpendicular to that plane, but the direction you choose. And then how much, again here, you provide it in the length, okay? So you type any number that you want, and let's say I wanted to extrude it for 50 mil, correct? And then say OK. You can even click on preview if you want. And OK that, and there we go. Now we have a what? We have the box. So this is a cube, which is also a right prism. Now let's say I want to change the shape of the profile. Instead of a prism, I want to make it, let's say, a cylinder, right? Instead of, sorry, a cube, I want to make it a cylinder. Well, what should I change? Yes, the profile. Instead of rectangle, I need to make it a circle. How do I do that? I need to change this sketch. So what I do is, if you see here, now this pad 1 has a plus. So if you expand it, you can see the sketch underneath. And if you double click on the sketch, you go back to the sketch that you made. Now, if you want, you can delete this and then draw a what instead? Yes, draw a circle. Now, if you get out, the part, the pad, the extrusion will be updated like that. Okay? So you can change the sketch. Now, let's say I want this to be taller. So tall, which means the amount of extrusion, was provided in the pad window. So I double click on the pad window or the item, and the window reappears, and then say I want it to be 120. Yeah, and there we go. So if you want to edit the 3D features, you click on pad. If you want to edit the sketch, you double click on the sketch. Okay, so this is the simplest thing you do in CATIA. Now, as I said, if you double click on this pad window, it has more options. It has a lot more options. One of them is thick and thin. So sometimes you want to extrude this sketch upward or downward, but you don't want it completely solid. You want to give the wall a thickness and make it a thin feature. So then check this box says thick. And then here you can see two values of thickness, thickness 1 and thickness 2, which is internal and external thickness. So let's say I want 4 mil thickness and say preview. Yeah, did you see? So this is the inside thickness, and then let's say maybe 2 also units outside. And you see this one is the outside of the sketch thickness. So the first one will be the wall thickness, which is measured from the sketch inward. The bottom one is measured from the sketch outward. So if you do that, it means 6 mil thickness, 4 inside, 2 outside. And there we go. Now you have a shell, you have a hollow object. Okay, so this is another way to do it. Now double click on this guy back, right? And uncheck the thick so that you can get the solid cylinder back, right? What other option do you have? So we learned that we have thick, we have reverse direction, we have the dimension and the value. The other thing you have is mirror extent. Sometimes you need to extrude both above and below the sketch plane and in a mirrored way. So if you go 120 above, you also want to go 120 below, then all you need is click on mirror extent. Okay, and look. Now it's exactly the same amount above and below. Sometimes you don't need to go exactly the same amount above and below. You need them to be different values. Then do not check this. Instead, click on more. And now you have what? First limit, which in this case is in the direction of arrow, 120. And let's say you want 50 units below the plane. So here you come here and say what? I want 50 units in the second limit below the plane. And now look. Yeah, so you can make it asymmetric with respect to the sketch plane. The other thing you have is, remember I told you that you can make right prism objects, or you can make what? Oblique. So the default in CATIA is right. You always go perpendicular. But what if I want to make it an oblique cylinder? How do I do that? Where is the option for it? So the option is here, direction. You see, for the direction, the check mark says normal, means perpendicular to the profile. But if you don't want it, you can uncheck this. And now here you have to provide a line along which the extrusion is going to happen. Now here you have not created a line beforehand so that you can choose it. But you can make it right now if you want. How? So you see here, if there was a line, I could click on it and then choose it. But again, since there is no line, this is what I do. I right click here. And then I say, let me create the line right now. And it says, fine. How do you want to do it? Do you want to choose 2 points and then say go from point 1 to point 2? I say no. Actually, I want a different way. Although you can use point, or you can use point direction, or any way, or normal to a surface, or anything that you want. Let's, for the simplicity, say point to point. Then it says, okay, where is your point 1? And let's say I click at the origin. Say that's my point 1. Says, okay, where's your point 2? But I don't have any other point here, so I can create it again. I right click and I say I want to create a point. And then it says, okay, where do you want it to be? And I said, well, I want it first to be on this front view YZ plane, and then I say here at this point. Okay, you can provide the exact numbers for H and V. Let's say I wanted this number, and I OK that. Yeah, so now that I define point 1 and point 2, it creates a line for them. And now if I OK this, now it says, okay, I'm gonna extrude it for you in that direction. And there we go. Yeah. So now I have my oblique cylinder. So these are some of the options that you can have when you do the extrude. Now it has more options. Okay, it has more options. Let me show you what I mean by more options. So this is what I would do. So now let's say I want to get rid of this cylinder for the moment. Excuse me. I want to get rid of the cylinder. I don't want it anymore. So how do I do it? Let me first delete the line. So if I want to delete the cylinder, I right click on this pad and I say what? Delete, right? But when the window appears, I'm sorry, there is this important thing here, this check mark that you have to pay attention to. It says delete aggregated elements. What does it mean? It means not only delete the pad, the extrude that you made, also delete whatever was underneath this plus sign. So it will also delete the sketch that you used to create this extrude. So it will delete the 3D feature and the 2D feature. And if you do it, there we go. Everything is gone. Sometimes you do not really want to delete the sketch. You want to keep the sketch. You just want to delete the 3D feature. If that's the case, then when you do right click and delete, and it says, do you want me to delete aggregated elements? You say no. Just delete the 3D feature, not the sketch used for it. Okay? You see? The sketch remains. So that's one of the important things. When you delete, make sure, if you don't want to delete the 2D features, uncheck that aggregated element. Okay, so this is now what I do. I want to show you one more option, at least, that is there for extrude, and that is basically up to surface, which is a very nice one. So this is what I will do for you. I go here onto this plane, I draw a circle, and I extrude it, mirror extent like that. Now let's say what you want is, you want to extrude this circle all the way up until it reaches what? This bigger cylinder, right? So if you choose this sketch now and then click on pad, let me show you from the side view. The problem is if you provide a fixed dimension, what happens? You can see here that this extrude will go inside the other object. You don't want that. You don't want this portion that the two extrude have basically overlap. All you want is this extrude continues until it touches the surface and then stops. Okay? But if you want to do that, then you cannot provide a fixed number. Why? Because different points on this profile will reach the surface with different amount of extrusions, right? This guy will probably reach the surface at 80 mil, while this guy will reach it at 110. This point here will reach it at 105, and so on. So you cannot provide a single number for all points to just touch the surface. So instead of dimension, you say up to next, which means get to the next object that you see and stop, or you can say up to surface, and then it says, okay, what surface? And you say this surface. You click on it and look now. Yeah, you see? So this extrude now just went all the way until it touches the surface, and it never went inside. How do I know? I use wireframe. Yeah? So if you look at wireframe, you see there is no penetration here. The amount of extrusion is just enough to touch the surface. Okay, so this is basically using up to next. Okay, so we have seen different options, and I'll tell you later about up to, last, and so on. But these are different options for extrusion. Now, there is the exact opposite of extrusion, which is this guy, cut extrude. Here we call it pocket. So this one, instead of creating a prism, it will hollow out a prism. So let's say here, for example, I can click on any now that I have these extra flat surfaces, not only I can choose my original planes, I can also choose what? Any of the new surfaces that are flat, and I can draw a sketch on these guys now. So I choose this one, go to sketch, fit all in, and then let's say I draw something. Let's say I draw a hexagon or something, right? So I go to the center of this, then I draw a hexagon, and then I click on cut extrude, and then say, hey, cut for me out of this object in a normal profile, normal direction, 120 mil, right? And now look, I have what? I have this hollow object. So in addition to providing a value for dimension and just cutting for so many millimeters or inches, you can basically say, I want this hole to be through the object. So in order to do that, you either need to, let's do it on this hole. You either need to make this dimension more than enough to basically pass through the entire object, right? So if I don't remember how far I extruded this, I just keep increasing this number until I see this preview gets out of the object. Okay, so I say go ahead and keep increasing it, right? Until the cut extrude comes out of the object like this, and then I do it. Another way is, instead of keep increasing this and until it completely passes through the object, or you exactly know how much you extruded so that you do the same cut extrude, you can say, I want it up to last, which means throughout the entire object. That will find the amount of extrude itself and do the job for you. Okay, so that's this option, up to last, which is a very good option. So as I said, everything you do with extrude, you can do the opposite of that with cut extrude, create hollow prisms basically. So that was the first method of creating objects, extrude and cut extrude. The other way that you can create objects is if the object has an axis of symmetry, an axis of revolution, like a sphere, an ellipsoid, a torus, or anything like that, even a cylinder, right? Those objects, you can rotate them, or we call revolution, around an axis and create a rotary object. Let's say, for example, if we want to make this donut shape, how do we do that? So the way to do it is, let me get rid of everything here and start from scratch. So I come to the side plane YZ, and then I would draw a circle but off center. Okay, so on the x-axis is the center of the circle, but it is not centered at the origin, like that. Get out, right? And then instead of using the extrude or cut extrude, I come to the third command, which here is called shaft. Shaft is the same as revolution or rotation. So I say I want this profile. So it says, which profile is that? You see it's already selected. It's sketch number 4 that we made. It says about which axis do you want to rotate it, and here I choose this vertical axis, and there we go. I got the donut. Yeah? So as simple as that. Now, sometimes you don't want to do the revolution fully. You just want the partial revolution. There, you can provide, let's say I just want 270-degree angle. And there we go. You get this shape. Okay, so you can provide how much of revolution you want. You can also, if you want, make it a thin or thick object. So let's say I want 3 mil thickness inside. So you can make this kind of pipe. Okay, so it gives you a bunch of options. And then opposite of that, you can do this command called groove. Groove is like cut revolve. Okay, groove is like cut revolve. So you draw a profile, revolve it, and hollow the object with it. For example, here, I go back to this plane, and here I draw a rectangle like this, get out, and I would rotate this guy about this axis, and then hollow out the rest of the material that I have created so far using this sketch. And look, if you do that, now you would get this guy, right? So this is the cut revolve, basically. So revolve and cut revolve. Now, some objects you can create by extrusion or revolution, like a cylinder, right? A cylinder can be done by extruding a circle, or if you do a rectangle, which is half of the side view of the cylinder, and revolve it about that axis, you can get what? You can get a cylinder. Now, about cones or truncated cones, you easily can draw a triangle and rotate it about the vertical axis to make it a cone. But if you want to do it with extrude, it's not actually a prism. A cone is not a prism, because as you cut and with horizontal planes and go up, they're all circle but of different sizes. So it's a kind of extrude that is drafted. So you need to also provide what? A draft angle to the extrude command. And the thing is, the simple extrude that we have, the simple pad command that we have, there is nowhere in it that you can also provide a draft angle. So you cannot do it with this extrude. But if you expand this guy, there is another version of it, and there is another version of it. These two versions are quite interesting. Drafted, filleted pad, and multi-pad. Okay, so I'm going to explain them in a second. But using the middle one, you can give it draft, or there is actually directly a command called draft, which is in this other dress up toolbar, this third one here from the top, this guy, which when extrude is created, you can then apply a draft to it. So then you can create a cone if you want. So let me show you those before I move any further forward. Let me show you some of the new stuff. So let's look at, for example, the drafted filleted pad. So this is what I do. I go on this XY plane and I draw a rectangle, get out, and now instead of a simple pad, I choose the middle one, drafted filleted pad. And this guy is quite interesting. First of all, it is asking you how far you want to go. Second of all, it says, okay, now what draft angle do you want? 5 degrees, 10 degrees, or so. And it can also fillet the edges of that prism for you. Now, if you don't want the edges of that prism to be filleted, turn these guys off. So it only gives it the draft, no fillet. And I'll show you what it would do, but you don't get rounded edges, you would get sharp, straight edges. So first, let's see how it might look like. So it says limit, and I use the bottom plane as the limit. And here, let's change the angle. Okay, let's go to 15 degrees and look at the preview. Yes. So as you can see, it provided this kind of shape, but you see that when you say my second limit is this plane, actually the size of the profile on that second limit is the one that is the same as original sketch. The original, on the original plane, the size will be basically modified to accommodate for this much of height and this much of angle. Now, this is clearly a draft inward. You might also provide a draft outward by changing the angle from 15 degrees to negative 15 degrees. Now, it is clearly drafted outward. Now, let me bring this height down to maybe 60 mil so that you can better see it. So this is the preview now, you see? Here it is negative 15, so the bottom sketch is smaller than the top one. If you make it positive, it's the opposite of that, right? But in both cases, the end profile is the same size as the sketch that we made, not the original, the bottom profile. Now here, you see it says neutral element first limit. Now, if you change that to second limit, what happens? That is probably what you want, right? You want the object at the base to be the same size of the sketch, but as it goes up or down, it is drafted upward or downward. So that's probably what you want. And now you can increase this angle and see the effect, right? So that is how you create this object. Now, if you say, I want the edges to be filleted, then this is what you get. You see, now all the edges are rounded, filleted. If you don't want them, you just don't do it. Make them sharp edges, right? Like that. Now, if you want this instead to be a cone instead of a truncated pyramid, you double click on the sketch and change this guy to what? Yes, to a circle. So if you draw a circle, okay, and then you have to go back in the draft and redefine everything. Not this one, of course, so let me get rid of this. This one, let's redo this. So I use this, I go with this one. I use the second limit. I use my limit plane to be the original plane. And I look at the preview and I get rid of the fillets. So as you can clearly see now, this is what? A truncated cone, and I can change the angle to make it a cone, or I can increase the height, right? If I know exactly how high I should go, what is the size of the base, then I can calculate the angle needed to make it a full cone, right? So if, for example, I say here 100, still not enough, maybe 120 is more than needed, not even 130. You can mathematically calculate that, okay? And there we go, I got my cone. Now, of course, you clearly see that this cone, as you see here, instead of being completely round, it is like faceted, right? You can see different flat faces, and that is this performance that I told you. Remember the 3D accuracy? If we went to Tools, Options, and then under Display Performance, right here, these two numbers, especially this one, 3D accuracy is 0.2. So if I make it a small number, like 0.02, I expect it to show me a little better cone than this one. Okay. Maybe not really. I need to go further down. Let's make it really small, see what happens. Can give me anything better. There we go. Okay, so this is better resolution. Of course, it makes my computer run slowly, but it can give me a better visualization of the cone. You will never get something perfectly round. It's not possible because you can never, as I said, ever create a perfect circle. Any circle that you draw in any CAD software is actually a polygon with a bunch of edges. Okay, so that's fine. Okay, so I showed you how to do a drafted filleted pad. Now, as I said, you can create a pad only, and then you later use this draft command and draft it separately. Okay, so that is possible too. So for example, here, let me show you. Right, so this is, I just made a cylinder. I used this command and made a cylinder, right? And I didn't use the middle command. Then, as I said, I can come to this dress up toolbar and I use the draft command, then provide a draft, and then it says, what face do you want to draft? I say this guy. It says, what is your neutral element? And then I say this one. And then, yeah, you have to make sure that you don't make a mistake and select two things for one. So you have to come here and say this is neutral element, 25 degrees, and then do what? A preview, right? That's what you get. Or if you want it inward, instead of 25, you make it what? Negative 25. And there we go. Yeah, so you can do it separately if you want to. Okay, so now we have seen these 4 commands and draft all together. There is one other type of pad that I want to show you, and that is a multi-pad, this guy here. So let me show you that as well, and then we go forward with the rest of the commands in this toolbar. So here, let me delete this pad too. If your original sketch has several basically close profiles, so let's say something like this, right? You have now 2 profiles in the same sketch, 2 close profiles in the same sketch. Can you pad this? So if I select this and say, hey, pad this for me, what does it do? It applies the pad to the whole thing, but that circle is considered as what? As a whole, right? So you get this guy. Yeah? But what if you didn't really want this? What if you wanted the rectangle to come up so many units, but also the circle be padded up instead of being considered as a whole? Maybe you wanted the circle to come up like 20 units, 50 units, or 200 units, right? So you want each one of these close profiles to be extruded with a separate amount of extrusion. You don't want one of them to be like the general sketch and be padded and the rest of them be considered as a whole. So how would you do that? That's where you use this guy called multi-pad, okay? So you can extrude different parts of a sketch, different profiles of a sketch differently with different amounts of extrusion. Okay, so let's take a look. So here we go under extrude, and then I've used this multi-pad. Then here we select our sketch. Now it recognizes here that there are 2 profiles, so it allows you to provide 2 different values for extrusion. So first you click on this one, which is the rectangle. Then you say, I want this guy to go up 60 mil. And then you click on this one, which is the circle. Say I want the circle to go up 20 mil. And look, there we go. Yeah. So you clearly can see that. Or you say, no, I want the circle to go up 80 mil. So it gets out of the cube. There we go. So you can do multi-pad, and this is a really nice, convenient tool. Instead of doing several extrudes, you can do the sketch first and then one extrude for all. Otherwise, you have to do 2 separate sketches and 2 separate extrudes. Here, you do 1 sketch and 1 extrude, while your sketch has all of the profiles in it. So it's a very good, useful profile. Okay. So what else do we have? So there are some other tools in it that we have to look. So let's go and take a look at them. So this command here is called hole. And hole is for creating standard holes, standard drilled holes. So let's say I want to create a standard drill hole on this top surface. So what I do, I click on this command and then click the surface that I want, like that. And then it gives me this window using which I can provide the specs for the hole. So I say, what is the diameter of the hole? 10 mil. How far do you want to go? Maybe 30 mil, right? And then do you want to drill normally down or at angle? You can do that. Then what do you want at the bottom? Do you want V bottom or flat, right? Do you want the bottom of it to be flat, or do you want it to be like when you use a standard drill bit, the bottom of it is V shape at some angle. The standard angle is 120. So you can do that one. Then not only that, you can also use for type. So not only you can do a simple drill like this, you can say, I want a counterboard. And in counterboard, the top of it is a bigger cylinder. And why would you do such a thing? So this is where you want to use a screw and screw something on the surface, and you want the top of that screw to be what? Flush with the rest of the surface, okay? You don't want the head of that screw to stick out of the part. You want it to be flush. So that's what you do. If the head of that screw or bolt is what? Cylindrical. Sometimes the head of some of the screws or bolts, not the bolts, screws, are what? They are conical. So instead of counterboard, use what? Countersunk, right? And in countersunk, you see that the head is like that. Okay? And then look, if I do that, now a standard, and I can see it under wireframe, a standard countersunk hole with the drill bit is created in the part. Okay? So you might say, well, if I want to cut out a hole in an object, can't I do it with the cut extrude? All I need is to draw a circle and cut it down. Sure, you can. And actually, cut extrude has more power over hole, because not only you can cut out a cylindrical volume out of the part, you can cut any other shape, right? So the cross section can be trapezoid, can be hexagon, can be any shape. So pocket is more flexible, of course. You can do any shape and then cut it out. But first of all, this is not the standard drill. This is just an arbitrary shape. And whatever shape that you make here doesn't mean necessarily when you want to manufacture the part using a CNC machine or something, you can easily do it. Okay, especially if all the corners are sharp, you can never achieve that. You need a little bit of roundness in the corners for any milling machine to be able to mill it for you. Okay, so just keep that in mind. Since that is an important point, let me just tell you, if you want this object to be created, okay, and then you go on this surface and let's say you draw any shape that you want, okay, like a parallelogram, like that. Get out and cut extrude this guy. Okay, so yes, you can create this fancy feature inside the object like that, a parallelogram cut. But when you want to create that in a CNC machine, it's not just that easy. So remember, whatever that you create in a CAD software very easily using these tools, it doesn't mean you can replicate in the real world using the machines that we have. No milling machine can ever give you perfect sharp corner like that. You always need to separate a small amount of radius for the radius of the mill tool, okay? So if you really want something like that, then the closest you can get in real life is if you do fillets on the sharp ends, okay? So you have to do a little bit of fillet, something like this. How much is that? Depends on the size of the tool that you're using. But it is really impossible to create such sharp corner in real life. So you might be able to get something like this, okay? But if you want it perfect sharp, it's not doable with a milling machine. So just wanted to remind you about that very important point. Now, what's good about this hole command? As I said, it's only for standard cylindrical holes. The good thing about it is it does not need a sketch, really. You don't need to draw a circle for it. You just provide the depth and the diameter and it does it for you. Second, this command can create for you this countersunk and counterbore heads that the cut extrude does not do it unless you do two separate cut extrudes. And more important than that is, let me show you, is you can create threads. Okay, so not only you can drill it, you can provide threads. So you see this one is not threaded, but if you check this, now you can provide what? Thread. Okay, and you can say what type of thread I want, whether I want metric thin pitch or thick pitch and so on. And then you provide the type of the thread. I want M1, M2. Of course, the dimension of it should match, right? Because the diameter you have provided here is separate number, then standards. And then you can create a right-handed or left-handed thread and so on and so forth. Now, of course, this was M1, and M1 is not absolutely a good number in this case, so you definitely need to go up, something like M3 or so, even more in this case. How much, we'll talk about the threads later, but just want you to have some idea. So now this drill hole is threaded, but one thing that you have to notice is the threads that are created by this command hole are not visible threads. Those are just cosmetic threads. What does it mean? It means if you look here inside this hole on this lateral surface, you do not see any visible thread. It's there, it exists. How do I know? I'll show you 3 different ways later to find out if there is a thread somewhere or not, even though it's cosmetic, but you don't see visible thread here. Can you create visible threads in CATIA? Yes, that is using this command, basically cut sweep, which in CATIA we call slot. I'll show you how to do that. But this thread created by the hole command are cosmetic. You don't visually see them. You know they exist for several ways. One is, if you look at this hole, if you look at the symbol of this hole, around the circular hole, there is this 3/4 of a circle line, black line. That symbol means the hole is threaded. Of course, you can double click on the hole and see that the thread option is on. Now look, if I turn it off, you see that 3/4 circle is gone. So whenever you see around the center hole in a hole symbol, there is this small black 3/4 circle around it. That means the hole is threaded. That's one way to basically find out if it's threaded or not. The other way is there is this tool down here on the bottom right, which typically is invisible. You have to bring it out. And get it out. Where is that? Oh, here. It's actually here. It has been displaced. So it's under analysis, and this guy here, it says tap thread analysis. Okay, this is used to analyze the quality and some quantities about threads and tabs in a physical part. And once you click on this guy, and it says apply this analysis to the entire part, if there is any threaded hole anywhere in the part, it will highlight it for me. You see here, this guy is highlighted. And now here, the depth of the thread is small, so hole depth, okay. So thread diameter and thread depth. Let me make the thread depth a little bit bigger. And now, again, if I do it, apply, there we go. So this command will highlight for you any threaded hole or threaded shaft here for you. So that's another way to figure out where in your part you have threads, other than the symbol. And the third one is later when we go to drafting environment. In drafting, if you create drafting out of a part in which there is thread, extra lines will be created on the standard views for the threads. And I'll show you later when we go to drafting how to figure out which one of those lines belongs to the thread. So I showed you about the hole command. Now, one thing about the hole command is if you expand the hole command, there is a sketch. Remember, I told you we don't need a sketch. But this sketch is not really the circle that you did a cut extrude with or something. This shows the location of the hole. Because when you click on the surface, CATIA did not ask you, where do you want me to put the hole? Do you want it at the center or do you want it off center? It didn't ask. You could provide it here, as you can see, if you go double click on the hole, here it says positioning sketch. That's the same thing as this sketch I just showed you. So this sketch would tell CATIA where you want this guy to be. Okay, not always you want it at the center of a surface. So here, I can double click on here or go to that positioning sketch. They are the same thing. And all this sketch is a single point, which is this point here. And if I move this point to here now, look. Now the hole is created elsewhere. And if I want it exact, then all I need is to provide dimensions, right? I say where is this point located with respect to the x-axis and with respect to the y-axis of that surface. And that's all you need. Okay, so again, remember that the sketch is the center of the hole, not the whole profile. Okay, so hopefully now you learned some basics about the hole command. Now, a few other commands that we need to know, and they are extremely useful and important. One is this command called rib, and then the opposite of that, slot. In other CAD software, we call them sweep and cut sweep, or swept cut. So this is a different thing than extrude. What's the difference between this one and extrude is here you have a sketch and then you have a guide profile or center profile, and your sketch follows the guide profile. And the profile, the guide sketch does not need to be a straight line. In Extrude, your sketch follows a line and creates a volume, right? Whether that line is perpendicular to the original plane or at angle, your guide profile is a simple line. Here, it can be way more complicated. It does not need to necessarily be a line. For example, let's say we want to create a pipe, right? So this is what I do. I go to, let's say, the YZ plane, the front plane, and then I create basically an S shape or Z shape guide profile like this, and I also fillet the corners like that. Okay, then now I want a circle to follow this profile and create a pipe for me, right? Or a hollow circle and follow a pipe and create a pipe for me. So this you cannot do with Extrude because this guide profile is clearly not a single line. So in order to do that, now that you have the guide profile, now you need the sweep profile, the one that you want to follow this path. And in order to create that, pay attention that this profile has to be on a plane where that plane is perpendicular to your path. So you cannot just go anywhere on any plane and create a profile. That's not going to lead to a good result. What you need is, as I said, a plane perpendicular at some point to this profile, and preferably you want that plane to be perpendicular to this profile either at the beginning or at the end. So none of the original 3 planes would qualify. Therefore, you bring this guy here that I showed you in the past and use the plane command to create a customized plane. So you click on this, then first you click on this profile, and you see right now it's offset from plane, but once you click on it, it changes it to what? To normal to curve. Say, okay, you selected the curve, so you want it to be normal to curve. You say yes. Then it says, okay, do you want me to put it at a specific start point? You say, sure. Where? Not the middle. I want it to be at this end point. And now you see that's the preview, and you okay that. So this guy is perpendicular to that profile at that point. Now I create my sweep profile on this plane. I click on it, go to sketch, and then I draw whatever I want. So let's say I want a pipe, so I create a circle like this, and then let's first say a solid object, then I make it hollow for you. So here, okay, and then now I click on the sweep command. Again, here it's called rib, and then it says what is the profile for you, and I say the profile is this guy, and then says what is the center curve, and I say this one. Then it gives you a preview of the object, right? Very well, fine, no problem. Now, one of the problems that happens with this sweep is if your profile is too big that when it passes through the center curve, it would intersect with itself, then you get an error and you cannot do the sweep. What do I mean by that? Let me show you. So if I go here and change this line, give it some angle, okay, let me do it again. So I go with the sharp angle like that, make it like real Z. Okay, and then I also fillet, okay, to help it a little bit, but you see here I have sharp turns, and then you see here it does not like it. Or let me undo this and redo it. That is fine. This plane has to be re-evaluated. Okay. So we select this and this. There we go. We go here. We draw our profile. Let's make sure I'm on the right side. Yes, I am. Okay, and then I draw a big circle. So now you can imagine when this big circle is going to follow this path at this choke point, the circles that are here would intersect with the circles that are on this inclined line. And so the profile would intersect itself. When this happens, CATIA doesn't like it and doesn't allow you to do the sweep. So we click here, we say this is my profile, this is the center curve, right? And you see, it says this is self-intersecting. Either increase the radius of the curvature of the path, so make it wider turns, or reduce what? The size of the profile. So when this happens, either change these angles to bigger angles so that you provide a bigger radius of curvature, or make this guy smaller. You make this guy smaller, then you can still do it. Okay, so it's very important then that you know what you're doing. Okay, maybe 15 is too small, 25 probably. Okay, so let's do it again, and we say I want this to follow that, and you can do it. Okay, because it doesn't intersect itself. So the sweep command is extremely powerful, and it gives you the chance to create way more complicated objects. Okay, again, we call it rip here, but and we can make it thin if we want to. Okay, so we can create a hollow object if the inner profile and the outer profile are similar shapes. So if I want to make a hollow pipe, I don't need the original profile to be two concentric circles. All I need is to provide some thickness here. Okay, and there we go. Now I got my hollow profile. Okay, now the opposite of that is this guy called slot, which we also call cut sweep. So here the profile would follow a center curve and hollow out the object, right? And an example of that is, let's say I want to go on that plane and then cut something along this path. So I go here and then I create a simple cut along it like this. Okay, and now I want this sketch to follow the path, which was this guy. And let's see if it allows it or not. It says selected profile and center curve led to a twist. Okay, so here your profile was too long and too big. It has that self-intersecting thing. So I have to basically make sure that it does not intersect. And maybe if I bring this guy down instead of up, maybe it allows it. We'll see. So I bring it like here and try it one more time. If not, then we have to change this shape. So we do a cut sweep of that with this one. There we go, it allows it, and look now. Okay, so now you can see this cut is done through the whole object. Yeah. So this is a cut sweep. Now we have more real-life applications for cut sweep, and I'll show you when we want to create the non-cosmetic threads, the ones that you can visually see, like this guy here. The ones that you can see, the way to do it is using a cut sweep. How would you do that? Well, your center curve is going to be a helix, and then your cutting profile are different shapes. A common one is a triangle, and the triangle follows the helix and cuts out the material along the helix from a cylinder and creates threads. Okay? That is what we call using a die on a shaft, or if it's a hole, we use a tap. So to create visual threads, as I said, we use cut sweep, and we're going to practice that inside the class. Okay, so we'll leave that for practice inside the class. Okay, so I showed you these two guys. The other two that are again complement of each other are multi-section and cut multi-section. In other CAD software, we call them Loft. We call them Loft and Cut Loft. And this is one of the most complicated CAD features because it allows you to create almost anything you want by connecting different cross sections to each other. So let me show you examples. Let's say, for example, here, I go on this YZ plane and I draw a centered rectangle like that. Then I get out. Now, on a plane parallel to this YZ, I want to create another profile different from a rectangle. And then I want to connect this rectangular section to that, let's say, circular section, and create an object with different cross sections, which we call a loft. Where would you see that? I'll talk about it. Let me first show you, and then we'll talk about where you would see that in real life. So first thing is, I want a plane offset from YZ plane. So I choose YZ plane, I click on the plane command, and I provide some offset. Maybe more, and then on this plane I go and draw a circle again centered at origin like that. And now I want to create, as I said, a 3D object where one side of it is this profile, the other side of it is this profile. The only way to do it in any CAD software is using this command called Loft or multi-section here, which is this guy. So you choose that, then it says, okay, what are your profiles up there? And you choose this one, and then you choose this one. These are my profiles. And now if you click on preview, first of all, it doesn't allow it. It doesn't like it. It says change your coupling mode to ratio. So what is happening here? So first, let me go under the coupling tab here and change my coupling method from tangency to what? To ratio, so that first it can do it. And I can see that here. Okay, as you can see, it's not too bad. It's a little bit twisted, but it could do the job. Okay, so first thing is, why didn't it like it and give me error? Second of all, you see it's kind of twisted, right? You see the twist here. This one is not like in front of that point, this point, and this point. This, you see a little bit of twist in this object. Can be untwisted and fix it? Yes, I'll show you. So as I said, this is a little bit more complicated than other tools, but it has more flexibility at the same time. So let's first see, what does that coupling and tangency mean? Okay, So when you say tangency means if you have this rectangle here, and then if you have this circle here, so if you noticed, there is one point on each profile that is considered closing point. So what it does is it comes here, and that is typically coming from where you click to choose that profile, but if you choose it from the spec tree, then a default point is considered. So let's say this is the closing point for this profile, and this is the closing point for this profile. So when you choose the tangency method for coupling, because what is loft in the first place? Loft is choosing some points, connecting them with a line or a more complicated profile, then going to next point. So let's say here it connects these 2 points using a line like that. Then it chooses the next point on this profile. Now I make the gaps bigger so that you can visually see it, and then it comes to this point here on this profile, and then connects them together again using a different line. And then moving these points along the perimeters of the 2 profiles and connecting with line, a lot of them, and then coming up with the surface. But when you start with the first points, how does software know if these 2 points are good points to be connected together? Let's start with the first point, the closing point that the software just creates on the 2 surfaces, or you choose by clicking on them. So are these 2 points, the red points, are good points to be connected? Why shouldn't this red point be connected to this blue point? What is it that makes 2 points a good candidate to be connected together? So if you use tangency method, tangency means what is the direction of the tangent line to the profile at that point? And the problem is when you have a profile that has sharp corners, or basically it's not a smooth profile, at those non-smooth corners you don't have a tangent line, because if this point was here, the tangent line would be vertical. If it was here, it would be what? Horizontal. While here on the circle, it continuously rotates and changes, right? So it's here, then it's here, then it's here, and so on and so forth. So this method says match those points together that they have the same slope of the tangent line. For example, here that is horizontal. If there is a point up there for which the slope of the tangent is horizontal, connect them together. But the problem is when it comes to the next point is again horizontal, while here you do not have any more horizontal any more point with the horizontal tangent until you come down to the bottom point. But you have a bunch of points on this line and on this bottom line, all of which they have a horizontal tangent. And then here you have a ton of points here and here with vertical tangent, while you only have 2 points with vertical tangent here. So for this point that has an inclined tangent, or this point, there is no equivalent on the rectangle. So matching tangent lines, matching the angles of the tangent line is not going to work. That's why it says the tangency is not going to work for me. Why? Because this profile is smooth, that profile has sharp corners. If it was an ellipse or another circle, well, if it was another circle, all you need is the extrude command. You don't even need the loft command. But if it was something similar to a circle, like an ellipse, then yes, probably an ellipse you can connect to the circle using the tangent method. because ellipse is smooth as well. But when you have smooth and non-smooth, that method is not going to work. It says use coupling instead. What does that mean? Coupling means, let me get rid of some of this. Coupling means you connect the first 2 points together regardless. You choose one closing point on this, one closing point on that, and connect. Then, when you want to decide the next 2 points, use a ratio. Ratio of what? Ratio of the distance between the closing point to the new point. So if this distance between these 2 points is L1, okay, this distance, the length of the arc between these two is L1, and then the entire perimeter of the rectangle is P1. So P1 is the entire perimeter of that. Then the entire perimeter of the circle is P2, and then the length of the arc between the new point and the old point on the circle, this length of this arc is L2. The ratio of L1 over P1 should be the same as what? L2 over P2. Okay, this is called the ratio coupling. In other words, if this ratio is 5% of the whole, if this length is 5% of the whole perimeter of rectangle, by choosing this point, which point should you choose on a circle? A point such that the distance between it and the initial point is also 5% of what? The perimeter of the circle. Okay, so this is called coupling, and it always works because you can always find the length of the arc and you can always find perimeters, regardless of tangency or anything. So this method works for all sorts of profiles, whether they are smooth or not. It always works. Now, what's the problem here? That's the twisting. If the initial points that it chooses are not well in front of each other and they are not well matched, then when it goes to next point and connect, and then goes to next point and connect, and so on, you see what? You see the twist, and that's what is happening over here. So the reason here for the twist is because the closing points are not exactly in front of each other, okay? Because the closing points are not well selected by you or by the software. You see here? For example, if I could choose my closing point, so here your closing points, let me show you, double click here. If you see your closing points here on the rectangle, that's one of the corners, and on the circle is here. And these points are not exactly like perfectly in front of each other. The angles are not well matching. Well, if I could do this, I put this closing point to be middle of the top edge, and then put this closing point to be the top point of the circle. So they are right in front of each other, or they are on the symmetry plane. Then that could change a bunch. So in order to do that, we need to replace our closing points and remove this twist. Okay, so how do we do that? This is what you do. You come here and right click on this closing point and say remove or replace anyone. So I removed it. Then I can create a new one for it. How? This sketch number 13, which was the rectangle, you see I removed its closing point, so now it's highlighted, which means this guy does not have a closing point now. I right click on it and then go down and say what? Create for me a closing point on this guy. It says sure. Then it allows you, by changing this length, to move your new closing point along the perimeter of the profile until you are satisfied with the location. There are different ways to do it. You can go distance on the curve, distance along direction, ratio of the curve length. That's the same thing I said, ratio. So it's up to you how you want to determine that, but if I can get it roughly above the v-axis, then that will produce a lot better result. So something like this, okay? So now this is my closing point for the rectangle. Now if I now connect that to this guy here, which is not on the top, it's gonna give me a bad twist, okay? You see now clearly there is a huge bad twist over here. But if I change this closing point to as well, that makes life really nice. How? So this is what I do. I right click on this guy and remove or replace it. Okay. And then I do the same method that I did for the other one. I change this length until the closing points come to the top point. You see right now it's this blue guy. So if I make this number smaller and bring it right above the v-axis, or right below that closing point 1, then something like that, I can make a very good connection, right? So you see now they are right on the top of each other, and now look. You see it's significantly better. The twist is almost gone. Okay, so this is how you do a multi-section and the meaning of coupling and closing points. Good. Some more stuff to know about the Loft. So you saw that Loft has some stuff, right? It has profiles, then it has coupling, and it has some more items, but the one that I want to talk a little bit about is guide. Guide is what? If you remember, I told you that these different points are connected using a line. They are straightly connected by lines. And you might wonder, what if I don't want to connect them by a line? What if I want to connect them by an arbitrary spline or something? All of them with the very same spline, okay? Is that possible? And the answer is yes. And those curves, you create one of them, those are called guides. So these two guys are profiles. Those lateral curves that's used to connect the points together are called guides. Okay, so how do we do that? That makes it a very complicated shape, but very well at the same time. So let's take a look at this one now. So how do we do it? Let me get rid of this multi-section without deleting the profiles. So I have this original two profiles. Now it's time to create the guide. The guides have to be created on the planes that are perpendicular to the original two planes of the profiles. So if I did these two guys on YZ and parallel to YZ, now for guide I have to either use XY or XZ. So let's go with XZ. I have to see these guys from a lateral view. And then here I can create the sketch of the profile. Let's use an spline, a spline. Now the very important thing about the guide is intersection with the original profiles. So if I do something like this, it's not gonna like it. It says that your profile should intersect with the two profiles of the Loft. Okay, so this point should be on the top of that profile as well, and this point should be coincident with this guy. Otherwise, it's not going to like it. It says your profile does not, your guide does not profile with does not intersect, I'm sorry, with the profile, and it does not allow the loft to be created. So intersection is important. Now, when you do that, if it's something like a rectangle here, you can easily start at that point of the rectangle, right? But when you go to the circle part, that's the problem. When you go to the circle, you cannot really force this line. You see here, let me show you again. When I started on this top point, I got the coincidence symbol, right? Look here, okay? I know because of this double circle that appears on the mouse cursor, my point is on that profile. I get what? Coincidence. But here, I don't get it. So I cannot really enforce my point to be on that profile. So I'm gonna have some problem here. So before I do this, then this is what I do. I create a point up here, and then later I will force one end point of my spline to be coincident with that extra point. How? So I click on the point command, 3D point. I don't need to go to a plane or a sketch or anything. It says, okay, what do you want? I say I want it to be on this curve. And it says, okay, where do you want it to be? I'll try to make it on the very top of it. So let's see. So if I can make it exactly on the top, that would be nice. The problem is if you say ratio of curve length and make that ratio like 0.25 or something, it is measured from this arbitrary new point. So that might not be easy to do, okay? Unless, so here I said I want it on this curve. I want to make sure it's exactly up here, okay? It's on the v-axis, right? So if I just say, hey, I want it here roughly, visually, I want it there, I'm not sure if this point is exactly above the origin or not. Okay, and that's an important thing. So can I constrain that point and this axis to be on the same direction? We have to see here. It allows apparently coincidence, but no, it did give error. Why? Because they are not even on the same plane. So you have to make sure that the point that you create is exactly above the v-axis. So just providing a number of length and ratio is not going to ensure that. So what I do to make sure it's 100% on the vertical direction is I use this plane. And I create my point on this plane. Now, if I click on the point command, and you see here, it's right above V, and then I bring it and also put it on this guy here. Okay, so now you see it goes up and down, but it's not on the circle yet. But if I click this and click the circle, let's see if I can enforce it to be on the circle. There we go. So now you have double coincidence, means it is coincident with the y-axis and coincident with the circle. So that's perfectly the location I want it to be. You see, I use double coincidence here. Now, if I get out, I will force the first point of my guide to be here and the end point of my guide to be on that point. Okay? And then I can repeat the same procedure for a bottom profile if I want to. So first, let me go to this plane, draw a sketch, use a spline. So I start here, then I draw a spline, and if you want, let me zoom in so that you can see better. So you see here, I just leave it like there, and then I would force this guy and this point, I do multi-select. I force them to be what? Coincident, right? So I have a coincident here. You can see the circle, and then I have a what? Another coincident here. This way, I'm sure that my guide is intersecting both of the profiles. And you can see it over here too. It is on both. You can see those black points. That is for coincidence. Now, let's say I also need a guide at the bottom, right? So this is the top guide. I need a bottom guide. Now, the main point is this. If you want more than one guide, the guides should be on different sketches. In other words, this sketch number 7, which is for top guide, you cannot, in the same sketch, draw the bottom guide. It doesn't take it from you. Different guides should be in different sketches, like different profiles that have to be in different sketches. Different guides have to be in different sketches. So you need 4 different sketches here at least. So what I do, again, I go back to this plane. I now create a point on the circle, but at the bottom of it, right? So you see here, this point is on the vertical axis. Now I force it to also be on the circle. I get out, I go to the side plane, and on a new sketch, I make my S-spline, the bottom S-spline, to be intersecting with the other profile too. Okay, now I have everything for the complicated shape. So now I choose multi-section. I choose my profiles. I make sure my coupling is ratio, because that's the only way this guy can do it. Then for guide, I choose, before I choose my guide, I make sure my closing points are good. You see, my closing points are not good. It will give me the twist. So first thing, before I do anything else, let me fix my closing points, okay? You have to make sure your closing points do not give you a twist. So I will create a twist. I can put it right there. Then this one also. I can put it right there. No. Okay. I want it right there. Okay, very well. By the way, the direction for moving along the profiles after closing points are dictated by these arrows. So these arrows should be pointing in the same direction. If one of them, the point goes to the left, and the other one, the next point goes to the right, you see a hugely bad twist. So make sure, if these arrows are not pointing in the same direction at the closing points, you force them to. By clicking on them, you can reverse their direction. So make sure they are both pointing in the same direction. Now the closing points are good, the profiles are good. Now I click down here in this window for guide, and I choose the top guide, and I choose the bottom guide, and hopefully it does it for me. Now seems like one of the guys, it didn't like it. Seems like it's the top guide that does not intersect with the top profile. So you have to fix that, okay? So let me fix it. So one important thing is when we did the intersection of the S-splines with the rectangle, this point, this first point of the S-spline is on the vertical direction, but it is not forced to be on this point. Okay, that was for the top curve and also for the bottom curve. So we need a double coincidence. So we need to choose this point, hold down, control this point, and force also the points to be on the top of each other. We need a double coincidence here. And hopefully now it will not pick on us and it will allow it to happen. Okay, as I said, this is almost the hardest thing that you can do in part design in CATIA. A multi-section with different shapes of profiles with lateral guides, okay, and removing the twist. So you really need to make sure everything is in good shape. That's what I'm trying to achieve here. Okay, the closing point is good, arrow's good. Now the top guide and now the bottom guide. There we go. Okay, so now you can have this very complicated shape. Now let's go to the philosophical question. Where is this guy needed at all? We make this complicated shape, or using this cut multi-section, we cut this complicated shape out of something. Fine, where would you use it? Well, there are so many things. Actually, many of the things that you see in real life are loft. Like what? So your AE students, one of them is fuselage. So fuselage of an airplane, if you look at it, it's a bunch of basically ellipses and circles that are all connected together, right? So if you look at the fuselage of an airplane, so you have like an ellipse here, then another ellipse there, and then a little bit maybe circular there, and then something there, and these are all connected together. Okay. Also, the wing of an airplane, as I told you, there is this airfoil where it attaches to the body, and then the tip, so this is the root, this is the part of the wing that is attached to the fuselage, but the tip of it, which is exposed to the air, is not typically the same size and the same shape as the root. It's a different shape and it's a different size. And when you connect these two together to create the wing, you need the multi-section. Another thing is, if you know the basically tip of, let me do it again. The tip of the flathead screwdrivers, right? So what do you have in a flathead screwdriver? At the tip of it, you have a very narrow rectangle, while when this guy extends out, you actually have a what? Have a shaft, right? So you are connecting really a circle into a narrow rectangle. That's the tip of many tools, including a flathead screwdriver, right? Or a Phillips or something like that. So most of the stuff that you see actually in real life, if you cut them at different heights, you definitely, or different length, you would definitely see different shapes at the cross section. Also, if you look them laterally, these cross sections are all not connected by straight lines. They are connected by complicated curves, like human body too. If you cut human body and do basically like an MRI section or something at different, from the feet all the way up to the head, you clearly see different sections, different shapes. So human body is another loft. Okay, so loft and loft cut are, as I said, two complicated ones. Finally, what we have is the solid combine, which we'll talk about later. One of the features that might be nice for you to see is this guy called Stiffener. And this is basically a wedge, a wall that connects two walls with different angles, let's say horizontal and vertical together, and connects them to stiffen the structure. Okay, and many times when you want to create this kind of feature, instead of creating a sketch and then extruding it, you can just draw a simple line and do it. Now, what do I mean by that? Let me show you. So let's say you have like a T-beam or C-beam or any shape that you want. Let's just make it simple for now. Let's make this 500. Still nothing. Make it a lot bigger. Although we don't need to, but just for the sake of the visualization. So let's say you have a structure like this, and here you want to connect these two guys together by a stiffener and reinforce the structure. Now, in order to make life easier, what I would do is I would make this like 400, and then I make it mirror extent. Okay, so I put this plane to be the mid plane of the structure. So now, as I said, if you want to create this kind of feature, what you can do is you can go, of course, on this mid plane, draw the profile of that, which is a triangle, and then extrude it both ways, right? So it's not a big deal. You can go here, and then I think I made this a thin pad. Let me 1 second, or it's a bad graphic. Yeah, I made it thin really. So you go here and you use a rectangle, and you make sure that rectangle edges are coincident with the vertical and horizontal edges. Like that. Then you get out, and then you extrude this guy. Let's say 50 units mirror extent, something like that. So this is one way to make the stiffener. The other way to do it instead of this is all you need is just this profile, this inclined edge of the profile. The rest of the edges are the vertical and horizontal. CATIA will figure it out. What do I mean? So you go on this mid plane again, but you don't need to draw the whole triangle. All you need to draw is a single line like this, which goes from here to here. And then use this stiffener command, and you provide some thickness, let's say 25 or 50. Okay, and there we go. Yep. Even those endpoints, as you saw, they do not need to be coincident with the vertical and horizontal edge. As long as all you need to provide is the angle, basically. It will figure out the rest. So look at this, right? There we go. So this is a good thing to do. And many times when this profile of the walls is more complicated, also drawing the sketch and extruding it takes more time, while just simply drawing a simple line and then using the stiffener command will make this creation a lot faster and easier. So hopefully now at this point you know all of the tools in the Sketchbase profile tool. Now we have some more toolbars and commands to see, including the dress up, including the transformation, this one for thickness, maybe this one for taking a picture, this one for dynamic sectioning, so there are some, and this one for measure. So there are some toolbars, a bunch actually. This one for applying material, then changing color and so on. So there are some stuff that, and later this one for catalog. We'll do the knowledge in a separate lecture for parametric design. But there are several other things that I want you to learn about part design, as it's the most complicated, not complicated, the most extensive part of CAD is part design. So let me go over some other stuff. So we have to cover these two toolbars, and then there are some other things that I mentioned. So I mentioned this deleting that do not aggregate, delete aggregate features if you don't want to delete the sketches. I talked about holes. So we need to talk about color and material, and this guy very important. Reordering, changing the support plane, and part definition modification. Okay, so before I go over the other toolbars, let me talk about some very important thing, very, very important, that can help you a lot along the way. So this is what I would do. First thing, you made a part like this. How can you change the color? What if you don't like this color, you want to apply a different color? So what you can do is you can change the part of the entire part. The color of the entire part can be changed to something, or the color of each one of these 3D features. Let me get back the stiffener. You can change the color of the stiffener to one thing and the color of this pad to something else. So you can have a multi-color part. Or you can change the color of the entire part to something. How do you do that? Let me show you. So if you want the color of the entire part to change to something from the default gray, you right-click on the part and then go to Properties window. Then you go under Graphics, and then for changing the color of the faces, you choose Fill Color. You can also change the color of the edges from black to something else, but let's not mess up with the edges right now. Just change this maybe to orange. There we go. The whole part has now changed color. Now you might say, what if I want each one of them to be colored separately? Then you right-click on that feature instead of the gear, which is the part. So I right-click on this pad, go to properties of that, change this maybe to light green, and then right-click on the stiffener and change maybe to light blue or something. Yeah, so you can have a multi-color part if you want to. So this is changing the color of a part or its features. Second thing is, what if you want to apply material to a part and render the object with material instead of color? In order to apply material, you need this single tool toolbar called Apply Material, which is always found down here. You click on this, and here you have a library of so many different materials, from construction, fabric, metal, painting. Under others, you have so many nice things. like even mirror. You can have mirror kind of thing. Okay, rubber, plastic. By the way, that's the only plastic we have in CATIA. We don't have like PLA, ABS, and other 3D printing plastics. In SolidWorks we do. Then we can have different kind of paintings and so on. Stone, right? So let's say this is a structure out of stone, and I want it to be out of, let's say, some marble. Okay, so I click on this marble, and then I click on the part, and then I say apply material and OK. Now you see the material is applied. How do you know? If you look under the tree, there is this material here. It says marble 2, but the part does not look as if it's made of marble because you're not shading it with material. In order to do it, you go here under the shading cylinder, and then you choose the third item from bottom, shading with material. And there we go. Now it is shaded as if it's made of that marble. Okay, so you have to put the rendering into shading with material, which is really nice. Okay, so this is also applying material. Now, some other things that are important for you to learn. So we learned any feature that we create, we can double click on their windows and change their definitions, right? So we can change any of the specs we provided when we created this extrude. We know that. So that part is covered, but there are two more things that are important. One is change the support plane of the sketch. The second one is reordering features and the priority of the features. So let me talk about those. So sometimes you made this extrude, and then you'll find out that, well, actually this sketch that I made, this guy here, should not have been started on the XZ plane. I actually should have started this on the YZ plane, which makes this guy rotate 90 degrees. Right? So you find out that you started your sketch on a wrong plane. What do? Are you going to delete the whole thing and start from scratch? Or is there a way to change not the sketch, but the plane on which the sketch was drawn? Is there a way to do that? Yes. How? So you first expand the part to see the sketch. Then you right click on the sketch and go down all the way to sketch object, and then you say what? Change sketch support. If you do that, it says, okay, it was on XZ plane. Do you want to change it? You say, sure, I want it on YZ plane. And you see what happened? It just was transformed onto YZ plane. And now, there we go. Yes? So just as simple as that, you can change the sketch plane, not the sketch itself. So this is a very nice feature. Now, of course, we can rotate the object too. I'll show you later here that you have the rotate feature. We can rotate it, but then you have to rotate everything else. So I recommend you go with changing the sketch plane if you catch it early on. Okay, now two more things about any feature is these features, sometimes we do not want to delete them. So sometimes some stuff we do not want to delete permanently. We just want to basically treat the part as if they are not there temporarily and see the effect, and then maybe put them back. Okay, so the goal is not to permanently eliminate or remove a feature, it's just to temporarily disable it so that it's not on the way. I can visualize the rest of the part, and then if I decide, I'll bring them back later. That is called deactivation and activation. let's say this is stiffener for a moment. I say, well, what if this stiffener is not there? What happens? Should I delete it to see, or I can just deactivate it temporarily? Yes, it's always a good idea to deactivate. So if you decide to put it back, you don't have to recreate it, because once you delete it, it's gone. But what you can do, you right click on this guy and go down all the way to object and then say what? Deactivate this for me. And when you deactivate it with its aggregated elements, you see it's not showing anymore while still there. I can put it back if I want. I haven't deleted it, it's still on the tree. How do I know that feature is deactivated? If you see here, there is this small kind of O, right? It's like a red O with a white area inside. When that guy is next to anything, it means that feature is deactivated. It's not deleted. I can right click on that guy back, go down to dot object, and then what? Say activate this back for me. There we go, it's back, right? So it's a temporarily deactivating. Okay, another thing when you right click on any feature and go all the way down to the feature's name.object is reordering. So as I told you in CATIA under the spec tree, each thing is in a chronological order from top to bottom. So the stuff that you created first are seen on the top, the one that you created last are shown at the bottom. Sometimes you need to reorder some feature. Let's say here, I created this pocket 3 after pocket 4. So pocket 4 was created on this face first, then pocket 3 was created on this guy next. Now, if I want to reorder them, so bring pocket 3 up and bring pocket 4 down as if pocket 3 was created first, that is called the reordering the items in the tree. Now, first of all, why would you do that? Second of all, how would you do it? Because it's a little bit tricky. So, first of all, why should you do that? The reason is, if you want to refer to something that is created after a feature, in the definition of that feature, you cannot really use it. Well, what do I mean by that? I mean, when in the definition of this feature, now in this case they are quite similar and they are independent of each other, but sometimes when you want to create a feature, you need a sketch, okay? And if you created that sketch after you created the initial feature and now you want to use this sketch that you created later to further modify it. For example, like a what? What do I mean by that? What I mean is you created, let's say, a loft using 2 profiles. Now, after you created the loft, later on, now you have some new sketch, which now you want to use as a guide to the loft, okay? So now you go and double click on the loft and say, hey, in the guide window, I want to also specify that use this sketch as the guide for this loft. CATIA won't accept it. Why? Because this sketch that you made for the guide was created after that 3D loft. So, in other words, you cannot, in the definition of anything, any feature, anything in CATIA, make use of the features, sketches, or other things that you created afterwards. Each feature can only take advantage and benefit from the features and sketches created before that, not after that. Okay? So, therefore, if you want that guide sketch to be used with this loft, and it was created later on, as I said, you cannot do it, but the method to go around it is you right click on that sketch and then go to the sketch name, and then say what? Reorder. And by reordering, you can bring that feature, that sketch, up to what? To before your loft. When you bring it before or behind your loft, now it is as if you created it beforehand. So now that loft can use the sketch. Okay? So it's messing up with the chronological order. It's an artificial changing in the orders, okay? It doesn't mean you necessarily made this after that or before that. You are forcing the time of creation to go before or after, and then so that any feature can use the previous sketches. Okay, so first let me show you how you do it, and then in the class I'll show you a nice example of the application of this. So first, let's say I want to bring pocket 3 that was created after pocket 4. I want to bring it before pocket 4. How can I do that? I right click on pocket 3, go all the way down, and then say reorder this for me. And it says, okay, do you want it to be after something or before something? I say I want it before something. It says before what? I say before pocket 4. So now it means bring pocket 3 to before pocket 4, and you okay that. And now look, 3 is above 4, as if 3 is created before pocket 4. But what's wrong here? Both of the pockets disappeared. They are there, but they are kind of like inactive, right? So when you reorder, it does a deactivation CATIA because you are forcing it. It wasn't really meant to be that you are forcing it. So in order to put these guys back and make them visible and be seen and active again, what you need to do is you right click on each one and then first deactivate it, although it looks like it's deactivated, but not really. And then you activate it again. So you do a deactivate, activate on each one of the reordered features. And there we go, they appear. And then you do the same thing for pocket 4. You deactivate it first, and then you activate it first. You activate it next. There we go, right? So they are activated, they are back again, and the order is there. So now if, again, these pockets are completely independent from each other, but if I want in the definition of pocket 4, if I want to use this sketch that I used in pocket 3, if I somehow want to refer to it and use it, I can. Why? Because this sketch was created before pocket 4, but I cannot do the opposite. So in the definition of pocket 3, if I want to refer to this sketch 25, which is created in pocket 4, I cannot click on it and use it. Why? Because this guy is created after that. Okay, you see? I cannot click on it. It's impossible to use it. But the other way I could, right? So when I came here, now I can, if I want, click on that. If I go to the sketch, I can check this one instead. Of course, it is gonna mess it up in this case, but I can if I want to. Okay, so that's very important about reordering. Okay, so we have seen material, color, and so on. Reordering, changing the support plane for a sketch. Now, as I told you, when we create the thread in CATIA using the whole command, that is actually a cosmetic thread. It's not an actual one. And as I told you in class, I'll show you how to do a cut sweep of a triangle following a helix and create visible threads. Now, if you remember, one way to create thread was you do it at the same time that you do the hole command, right? So when you created the hole, it gave you the option to make it threaded. Another option that you have is you just create the hole only, using, let's say, a cut extrude or even the hole command, and then apply the thread later on, although it doesn't have really any advantage. But if you have a part that you got from somebody else and imported it, then if you need to add a thread in the location of the hole, you can do it with this command. So let's say here I have this block, and then inside this block there is a hole like that and no thread. Okay, something like this. Then, so you see there is no thread here. Then there is, under the dress up toolbar, which we're going to see right now, there is this command called thread tap. And this is for creating threads on either a shaft to make external threads, like for bolts and screws, or internal threads for inside the holes. Okay, so it's using die or tap devices, right? And when I say die or tap, let me just show you. So this guy here that you can see, this shape here, this circular object with the profile inside, this is called the die, and dies will go inside this die handle, and then you basically rotate them, put them on the top of a shaft and keep spinning them, rotating them, and they will follow a helix and create the thread. So let me show you creating thread on a shaft using die. Okay, so that's what I said. You have the die inside this die holder, and you put it on the shaft, and then what? Keep spinning it. Here the turning machine is doing that. And then, as I said, inside that die there is the thread profile and there is the helical profile. So when you do it, that will create these threads for you. Okay, so that's the die, and that is the die holder, and it will create a thread on an external shaft. On the opposite of that, you have tap. So you can say create thread inside a hole using tap. Okay, so this is the opposite of that. Maybe this one. So here you have the device called tap, like this, and they are very sharp, basically, or you can see it here. They are very sharp, basically, steel for cutting. And here, this is another view of a tap. Then you put it on a tap holder, and then you insert it into the hole and keep spinning, and then what you will get, as you can see, is the thread inside the part. Okay, so that's what you can see here too. You can create thread inside the part using the tap. Okay, and this is another picture of a tap with the tap holder, basically. So this command here in CATIA is capable of doing both. Let's say here I want to create thread on this hole that does not have it. So I use the command tap, and then it says, okay, what is the lateral face? I say this is the lateral face I want to thread. And then it says, what is the limit selection? I say this guy here, if it allows it. Let's see. If not, I have to select this one. Now it goes up, which is what I don't really like about it. And then you can provide the depth here. Okay. Now this part of it that is in the empty air is not going to thread, of course. And there we go. Now it has a thread with so much diameter, so much depth, and so much pitch. And by the way, pitch in a thread is the distance between each thread to the next. Okay. So thread pitch. If you look at the thread, the distance between each peak to the next peak is called 1 pitch, okay? And that's the amount that when you rotate a bolt or a nut, let's say if the nut is fixed, you rotate the bolt. If you rotate the bolt 1 full revolution, the amount that the bolt goes forward or backward is equal to what? 1 pitch, okay? So pitch is another one of the parameters that you can choose. So this thread is with 1 mil, okay? But if you want, you can change the pitch right here and make it a coarser pitch. So basically bigger thread, and make it left-handed or right-handed. So when you turn it clockwise, is the bolt gonna go inside a fixed nut that is right-handed, or it comes out of the nut, it's gonna be left-handed, okay? Most of the threads that we see in daily life, they are right-handed. But this is a thread and it's created, but again, even this command, when it creates a thread, as you can see, is cosmetic. You cannot visually see that, okay? I mean, you can see there is a thread. If you apply that thread analysis command, it would highlight it. If you go to drafting, it will show it, but you don't see physical threads. As I said, if you really want to do that, you have to do a cut sweep, and we'll do it in class, but just wanted to tell you what this command is going to do for you. Okay, so from this toolbar, I have shown you the draft and tap. Let me show you a few other important things that would be really important and useful for you. So one of them is the fillet command here. So fillet means around an edge. So you can either select an edge or you can select the face. If you select the face, all of the edges of the face will be rounded with this radius or any radius that you provide, or you can only select one edge. Okay, so if I select this face and I say round any edge that is on this face with 5 mil radius, and I say okay, there we go. Right now you can see clearly. Let me show all of the edges. Might give you a better idea. So now you clearly see that the top edges are rounded, right? So that's one way to reduce the sharpness of the edges so that they don't cut your hand. And as I told you earlier, if there is an inner edge, by making a fillet, you can reduce the stitch concentration and increase the life of the part. So this is one type of the fillet, face fillet or edge fillet, okay? Now, what happens if you only apply to an edge? So here I applied only to this edge. You see it's not applied to the other stuff. Good. The other things we have about fillet is under fillet there are other types of fillet. This face-to-face we'll look at it later, but this tritangent is an interesting one. So here what this one does is it eliminates one face completely and then connects the two other faces together using a fillet. So it's a big fillet really. So here you say I want this top face and this bottom face to be connected together, filleted together, and to do that get rid of this face. And look, there we go. So it created a huge edge, but not on, it created a huge fillet, but not on an edge, on the whole surface, and get rid of the surface, okay? And created this, what we call tritangent fillet. So this is another type of fillet that you have over here. And also, as you can see under the fillet, when you select some edge like that, you can either say that I want the fillet radius to be constant along the entire edge, or I want it to be variable. So I want some parts to be filleted with bigger radius than the other parts. So then you can use what? Variable edge fillets. Okay, so this one is not going to be the same thing. So this one says the way I'm going to change it is according to a linear method or a cubic. So the radius changes linearly from one corner to the other or in a cubic manner. Let's say I want it linearly. So here you have one number here and you have one number over there. And let's look at these numbers together. So this number is 5, right? Let's say I want this size to be 5, but this size that is 5, if I double click on it, I want this to be 10. Okay, so now if we go back, this side's still 5, that side is what? 10, and look. Yeah, you see that? The radius of the fillet changes linearly from 5 to 10 along the edge. Or you can say I want to change it cubic. Okay, then it goes cubic, and you need to add 2 more points to find the coefficient of that cubic polynomial. But this is variable fillet. The other way, as I told you, to get rid of a sharp edge is chamfer, which is cutting it with an inclined surface, basically. So again, you can do it on a whole surface, so all edges will be chamfered, or on a specific edge. And then here you provide the diagonal length, and then you provide the angle of the fillet, and there we go. The chamfer, and there we go. Okay, so that is another tool for getting rid of sharp edges. The other tool we have is called thickness. So sometimes you made something and then you figure out that, well, maybe I want a little bit more thickness on this face or on this face or on this face. What should I do? Should I go back and change the pad or change the sketch or what? And not all parts are this simple. Okay, so if you want to go back and find what parameter to change to make it a little thicker, it might need to go and dig and find what parameter is related to that. The other thing you can do is just select the surface and say, hey, I want this face to get 1 millimeter extra thickness, or let's say here I want it to get 10 mil extra thickness, right? And look at this height, and now look how it changes. There we go, right? Or I want this one to be like 10 mil extra thickness. There we go. So this thickness tool is actually a very useful tool. Finally, we have in this toolbar shell. We're going to talk about delete faces later, but we have shell. Shell is a very useful tool if you want to hollow out the entire part and only leave a wall thickness for the entire part. So you make the part empty and leave a uniform wall thickness all around the part. Sometimes you can remove a face, sometimes you can keep it. So here I click on shell and I say I want a wall thickness of 5 mil uniformly on all the part, and I say OK. And now this part is hollow. How can I tell? By wireframe. So now this part is hollow, and the thickness of the wall all around the part is equal to 5 mil. So I made a hollow box, but completely enclosed. And how else can you tell whether this part is hollow, other than looking at wireframe? One of the tools that I wanted to mention later, but I guess it's good to mention it right now, is this dynamic sectioning, which I really like. So it's a virtual sectioning. You really do not cut the object, you just virtually do to see inside it. So I say I want to cut this object using this plane, and if you want to see it, maybe you want to rotate this plane and make it vertical like that. And now look, if I rotate this, there we go, right? And see inside it, and then I can rotate this plane, I can move it forward and backwards, right? And I can do a ton of things in it to see everything about the object inside it. And whenever I'm done with it, all I need is to click back on the command and turn it off, and it goes away. So it's a virtual sectioning called dynamic sectioning. So I could see it's empty. Now another way when you do shell is you can also remove one of the faces. You say, hey, I want this face to go away. and make it like a hollow basket. And look, there we go, right? So not only you give uniform thickness to all of the walls, but one of the faces you can eliminate, or some of the faces. And you can make a simple hollow basket out of a cube. So this shell command, we're going to see it's really useful many times when we want a uniform wall thickness. Now, could you also do this with the cut extrude? Sure, you could. But cut extrude has more power in terms of you can cut out anything that you want, and the thickness of the walls are different, could be different. You don't need all of them to be the same number. Shell, they all are the same number, but the shell, as you remember, as you saw, it does not need a sketch. When I want to create a hollow object with uniform wall thickness, I do not need to draw a sketch, and I do not need to know how far I should cut down to get this basket. All I provide is thickness for the wall and the face that needs to go, right? So it is faster and easier, but the limitation is the wall thickness has to be uniform, and the shape of the hollow out area is the same as the shape of the entire object, okay? So this is about shell. So now I assume that you have seen this guy here and this one, which is really good. There is this toolbar left we need to talk about, and a few more. So this transformation toolbar is an interesting toolbar. So you can do a lot more complementary actions on your part. Like what? Like, for example, you can mirror a feature or the entire part. You can translate, you can rotate, or in general, axis to axis transform of a part. Let's say here, for example, let me get rid of some of these and make it a little bit more interesting for you. So let's say, since this part has the planes are mirrored about it, I go to the top plane, I do a simple cut here. Okay, and say I go 30 units, and I do this, right? So you created this cut extrude on this object, and now you want a mirrored version of this to be created on this side, okay? So you want a mirror version here, mirrored with respect to what plane? With respect to the mid plane, which in this case is this basically YZ plane. So all you need to do is you go and click on the mirror, and it says, what is your mirroring element? You say this guy. It says, okay, what is it that you want to mirror? You say just this pocket number 5. And there we go. That's simple. Okay, so I can simply mirror a feature with respect to a plane. I can mirror the whole object if I want with respect to a plane. No big deal. Now, what's the difference between this one and this guy here? The symmetry, what it does, it moves the feature with respect to the plane to the other side, and it does not keep the original one. It just moves it. It does not create a replica. Okay, so let me show you. The mirror created another version of that on this side. Now, if instead I do the symmetry, then when I choose this guy, and when I choose, let's see, yeah, okay, so you clearly see that it brought it to this side for me. It did not keep the original version. So this is the symmetry. Now I can translate, so I can move a feature from somewhere to somewhere. I can rotate the, but it's not just a feature. These two are for the entire part. So I can say, well, I want to rotate the entire part. You cannot rotate the feature. I want to rotate the entire part about some axis. So I click on this. Then it says, okay, so you cannot select any specific feature. It's the entire part. About which axis do you want to rotate the whole part? And I say, right-click, Z-axis. says, okay, how much? And I say I want to rotate it 90 degrees. And there we go. Yeah. Or if you do translate, say, okay, where do you want to move it? I say I want to move it along, let's say, the x-axis. And it says how many mil? I say move it 20 mil in the x-axis. So it should move in this direction, right? And look, it does, right? So you can translate and rotate an object, move a feature from one side to the other, symmetry, the whole object. Again, this is an object, it's not a feature. It basically mirror the whole part with respect to a plane, but mirror it to the other side and does not create a replica. This mirror does, and the good thing with this mirror is not only it can do mirror of the whole part, it can do mirror about specific features. Okay, so one more time, I emphasize that these three guys here are for the entire part, while this one is for entire part or individual features. The other very nice things that you have are patterns: circular, rectangular, and user-defined. So let me show you, for example, the rectangular. So here, let me move this guy a little bit away so that you can see better. So let's say I want to repeat this hole all along this top surface. So what I say is, I want a rectangular or matrix pattern. It says, of what? I say, of this hole. It says, okay, in which direction? First direction. What is the direction? Say reference element for me is this axis, x-axis. Now, if it's the right direction, you click on reverse and make it the right direction. Then you provide the gap between each two features, and then how many of them you want, right? Then if you want to repeat it in a perpendicular or other direction, you go to second direction. For reference element, you choose another direction like this, and then you provide some spacing. So here I go 20 mil spacing and 3 instances, and look, there we go. I get a matrix or rectangular pattern of one feature. Okay, so this is really nice. I can also repeat a feature along a symmetry axis and do a circular pattern, and we'll do that in the class. So we can repeat a feature and get a pattern. Finally, what we need to know is the scaling or the affinity transform. So scaling is, when you click scaling, it is for the entire part. It says, what is your reference for the scaling? And I say, you need a point to refer to for scaling. And I say, I want the origin to be my reference point. And it says, what is your scaling ratio? And I said, make everything 80% bigger, 1.8. Look, there we go, right? Or if you want, you can make it smaller by typing a number less than 1. There we go. So you can scale. But again, remember, all the scaling is done with respect to a point. So you need a reference point. And what does that mean? It means if this is my object and this is the reference point, so every point on this object, every point, I measure the distance of that point with respect to the reference point. Let's say this is D1. And then along the very same line, I make this distance D1 to D1 times N, where N is that ratio that you are typing in. So for example, if N is bigger than 1, now this D1 is going to be bigger, so this point will come here. Let's say it's like 30% or so. Then this point also is connected to the reference point. And then this D2 is multiplied by 1.3, so it comes here along the same line. This point comes here, and then you repeat, right? This point now comes to here. This point comes to here, and so on. And then you connect all of these points together. And you say this object is scaled with respect to that point by a ratio of or factor of 1.3 or 0.5 or so on. Okay, so that's the meaning of scaling. And then you can do affinity transform. Now, affinity transform does the scaling differently in different directions. The previous one did the scaling in all directions x, y, z with the same ratio, not affinity. For affinity, you can do scaling differently in different along different axes. So I can say my origin, I want it to be this. My XY plane, I want it to be the regular XY plane. My X-axis, I want it to be the regular X-axis. And then now, along X direction, keep it as 1, but along Y direction, make the part wider. And along Z direction, make it basically smaller. So look, this guy becomes this one, right? You're using affinity, you can scale a part along different directions differently. And that is extremely useful in many cases. Okay. So I assume now I have also covered this toolbar. So there are a few more that I need to go over, so that I can claim that part design is mostly covered, except for parametric design, which we do in the next lecture. So when you make your part and you apply some material and your final part is over and nice, let's say you bring this guy in. So you made some nice part and then you rendered it with the material and it's ready to be sold basically. Now you want to, although there are allocated workbenches to that, but for the moment being, if you want to take a nice picture of this guy, then what you need to do, you can use this camera for rendering. Click on this. And then here, it allows you to set up some parameters, like what? This one is scene. So if you don't want the scene to be this guy, this sky or boring uniform blue, then you can choose any picture that you want and you can download from here or there you have and put that as the background scene, right? So let's say I am such a very loyal ERAU eagle, so I say I want ERAU Prescott picture to be my background, right, with the mountains and everything. So let's find a good picture. Let's use a stem building because that's one of my favorites. So we download this picture, right, and put it under downloads. And then here, you click on this to allow us to choose the scene instead of this background scene. Okay, just wait a second. And it should allow you to choose your background scene. There we go. Let's see if it allows it. So here you have some predefined. If you want, you can use those that are already in CATIA available. Or if you go under custom, here it says background image. And you can browse for this new image. Okay, and then you can say to stretch it to make it fit to the background. Then you can change the lighting of the scene. You see, you have a default lighting. You have all sorts of lighting. You can change the color of the light source. You can do background transparent, reflective. You can do a bunch of things on setting the scene. And then here You specify your rendering options. What quality of picture do you want? High quality, medium, low. If you want high quality, be ready for some time for the rendering. So I put it at medium right now. What screen resolution do you want? You can set that up. Then you go here to define the render area. If you don't want the entire background, you only want a portion of it, you can here select the area and say, hey, I only want this area, right? Or something else. So you choose how big of an area you want from the background to be rendered, right? And then let me just get rid of these guys. Then once you're good to go, then you would click on render. The size is going to be these many pixels. It starts to capture a high quality picture for you. Medium quality, not high quality. High quality takes more time to render, and it gives you a nice picture, which you can use for your advertising, marketing, so on and so forth. Okay, so you got it. Now you say save that for me, and I call it Bolt, and you can save it with any picture format that you want. Remember that JPEG formats are lossy compressions, so you lose quality of the image in JPEG. So if you want, save it as PNG, Portable Network Graphics. Okay, these are always better qualities. And then it's over, right? And now if you go to downloads and click on this, now you have your very nice picture. Okay, so this rendering is a very, very good tool. Okay, so I guess I clarified this one. The other few things I need to talk about, one is this thick surface. So the tools here are good. Later I'll show you when we do surface design. For example, with this guy, I can split a part using a surface or a plane and cut it in half or in several sections. Or here, if I have a surface, I can give it thickness and convert this surface back to a physical solid part like this. So this guy here, we'll deal with it later when we talk about surface design and generative shape design. We'll talk about that later. What really matters to me at this point is this guy, measure toolbar, where you can measure inertia, you can measure some distances and some dimensions. So if I click on this measure, and let's say I click on this circle, it tells me where is the center of it, how much is the radius, right? Or let's say if I click to measure between 2 points or any 2 geometries, so let's say I want to measure between 2 surfaces, right? So I want to know what is the distance between this surface and this surface, and it gives me the distance. It's 240 mil. So if you forgot some of the dimensions used, or if you got the part from somebody else and you want to do some inspection and measurement on it, I recommend you use the ruler or the caliper. They are basically the same thing. They are all under the same measure. And you can measure angles, you can measure distances, you can measure surface area, and so many other things, okay? Even you can go to customize, and in 3D you can measure angles. So once you click on customize, then you can do a lot more, right? So it really is a very, very useful tool. The other tool there is measure inertia. So once you click on it, then there are 2 versions for measuring inertia. One is 3D, one is 2D. The 3D is going to measure the inertia properties of the entire physical part. So where should you click? You should click on the gear part body. If you do that, it's going to give you a wealth of information, including the volume of the part, the area of the part, the mass of the part, considering the density of the material that you used, the location of the center of mass,
the moments of inertia, principal moments, so on and so forth. You can even customize this as well. It can give you principal axis, inertia matrix, and so on. And then you can even export those if you want as a text file. Okay, so these are very important things for engineering. And you know, calculating some of those moments of inertia or center of gravity for complicated volumes is extremely hard if you remember in your statics course, right? So when you have a complicated volume, calculating these numbers is extremely hard on the paper. So one of the ways that we can find moments of inertia for objects or the centroid of objects that we don't know, so some random part is given to me and I have no idea where the centroid of it is or how much is the moment of inertia for it, because those are not something you can easily measure on a scale or something. The way to do it is if I can reverse manufacture the part and create a CAD model of the part and then apply the same material as the part does, then in CAD, by one single click, it gives me all of those info. So this command is extremely powerful. So this is 3D measure inertia. You also have 2D measure inertia. This one is for measuring inertias for a surface. So somebody might say, well, what is the moments of inertia for the circular surface on the top? So you choose 2D inertia and you click on that face and it shows you how much is the area of that face, how much is, where is the center of area, and what are the moments of inertia for that face. Okay, so you can do 2D or 3D, and as I said, it is extremely useful in engineering. So I learned about measure, and the very last thing that I want to mention is catalog browser. So you can create any part that you want, but CATIA also has some pre-built parts like bolts, keys, nuts, and so on and so forth. They are not really complete. There are not a ton of them, but let's say there are some bolts that you want. You double click and they are according to some standard like ISO or something. And this bolt here is something that you want. So all you need is you double click, go to under categories, find the bolts. These are standard bolts that you want. And okay, once you select the bolt that you want, you right click and say what? Instantiate a component or instantiate as a new component. Okay? And if you do so, it should allow you to create it. If it doesn't, use open document or open as a new document. And then it should give you that part which is already made. So some of the parts, a limited number of the parts are already available in catalog browser of CATIA, and you can take advantage of them to accelerate your work. Not everything is there. As I said, if you look at it, it's mostly bolts and keys and nuts and pins and screws. You don't have gears in it or ball bearing or something, more complicated parts. So CATIA library is not the most complete library. However, I show you a good trick to get more complicated parts. So let's say you want a gear and that gear is not in CATIA. So what you can do is to go and look in libraries of other software for pre-built standard files like SolidWorks. So here I launch SolidWorks, and SolidWorks, if you go, when you open it, launch it under Design Library. If you click on it, then you go under Toolbox, and the add-in should be installed. If not, it takes a few seconds to install it, and then all different standards are here. Let's say you want an ANSI inch or ANSI metric. Then you go under that, and here you have more parts. Okay, you have under power transmission, you have gears, and then bearings are here too. You have also structural members and O-rings that you do not have, or jig bushings that you do not have. Let's say gears are one of the hardest part to make. So you go under gears, then you have chain sprocket, timing belt, pulley, and then the gears. And let's say one hard gear could be a bevel gear. So this is a bevel gear, pinion, okay, or this one. And if you open up this far, okay, it takes a few seconds, but once you open this complicated part that needs a ton of stuff to make it happen, then what you can do, you go to File and save it as a version that you can open in CATIA as well. So there are some universal file formats that almost any CAD software can open. And one of them is IGS, the other one is STEP. Now STEP basically keeps more information of the original parts. They are bigger files, harder to open, but yet you can open them. IGS is a little simpler. STL is the mesh file that I said 3D printer software would need, and there are some other files which we're going to talk about. But let's say I want an IGS, a simple file, although it's not super simple, but it's not as complicated as step file. So you save it as there, and now you can see that file if I show. Okay, so if I go here under my downloads, you can see that file, the IGS, which is only 1.4 meg. And now I'm going to go to CATIA and open that. So here we go to CATIA, we go to File and Open, and then open this guy. And it opens it for me, so I can easily see it and use it. Now it's not exactly like SolidWorks. It does not have a bunch of extrudes and cut extrudes, and I cannot really modify it, so I have to get it correct in SolidWorks before bringing it here. It imports all of them as a geometric set. We talk about geometric sets later, but now I have skipped all of the work of creating this part in CATIA and directly got it from SolidWorks. Okay. And finally, for the last parts of this long lecture, and I mentioned that over here, the only part that is left is this annotation, which is if you have a part, basically you can add annotation to it. And with annotation, which is a toolbar that is typically on the right hand side here, right now it is hidden on the right side, so we bring it back. Then you can click on any section of the part, and then here with this annotation you can add leaders, you can add flags with leaders and so on, and add a note. So for example, you can click here, then you can click here, bring it out, okay, and then type in a name for it and say thread. You can even add URL and external links to it, and then here, if I show you, I have added a basically flag with notes, and I added some annotation, or I can say, hey, mass of this part is this much, and so on and so forth. So these are some really nice 3D annotations. Okay.